Hey guys, what's up? This is an extra tutorial to cover some of the common problems on the in-class test. So before I start, let me just say that everyone should have their grades, right? You should be able to get them on Canvas, and you should also be able to see a few submission comments that I might have made to your test, just explaining, where you could have gone wrong or things like this. We had a problem with one student. Canvas just seemed to not think he submitted the assignment. We sorted that out, but if that happened to anyone else, right, if it just seems like your test didn't get submitted for some reason, email me and we can try and figure it out, okay? Sooner rather than later. I'd also say that to anyone who hasn't submitted every assignment so far, there's still time, okay? There's no late penalties in this module, and I'd really urge you to take advantage of the fact that you can just do homework and get free marks. It just means that you don't have to do it well in the final exam if you want to pass or you want to get a 1-1 or whatever, It's going to make your life easier. So submit any homework that you haven't. Um, there are a few different things on this exam that people really stumbled with. Um, I'm just going to talk about each one of them. I'm also going to tell you how I marked them so that you can get a bit of insight into why your grade might be the way it is. So you can see I've just written here the average on the exam was 67%, which is really good, okay? If you got over that, congratulations. If you got under that, it's not too bad. There's still a whole final exam that you can study for. And I'd say just take this in-class test as a learning experience rather than letting it affect your ego in any way. So, for question one, I'm going to start with um, part A. Okay, I'm going to do the marking scheme alongside these guys in green. So for question one, it was 1 mark for each part. And the big issue came from these two at the very end. And we'll talk about why. But before we talk about that, I want to talk about part A, which should just be fine for everyone. Okay? If you're not okay with part A, go to the first tutorial sheet, right? Or go to, I think it was tutorial, or sorry, I think it was assignment 1 that you also had this on. This should be fine, okay? Finding the point of intersection isn't that bad. For part B, I actually need to show you something because this was kind of a point of confusion. So, part B1, find a vector which is perpendicular to the plane P, okay? So here's P. You can see we're given P in normal form, okay? So some people would write that P is going to be defined by the equation 2x1 minus x2 plus 3x3 equals 4. Now, you should know from the lecture and from tutorials that the normal vector n is obtained by just reading off the coefficients of x1, x2, and x3. 2, minus 1, and 3. So the vector looks like this. Okay? Not too bad. Now, the confusion came from the fact that if we talk about a different plane, right, let's say I'm talking about a different plane here, it's going to be defined by the same equation, more or less. But I'm going to let it equal to 0 instead. And that means we should have the same normal vector here. Okay? 2, minus 1, 3. And, good thing is, if we think about what the normal vector is, the normal vector should be perpendicular to the plane, always. So, if I do n dotted with any x on the plane, I should get 0. So let's try and do that. If I do n 2 minus 1, 3 dot any x, so x1, x2, and x3, then clearly what I get is this thing, right? Which is my equation of a plane, right here. So it is 0, okay? N dot x is equal to 0 for any x on the plane. This makes sense, right? That's why the normal vector you get by just reading off the coefficients. So if we come back to our plane P, right, instead of this plane pi, and we try and do the same thing, if I do n dot x, this is going to be, probably know where this is going. So when I do this out, this is going to give me 2x1 minus x2 plus 3x3. But for this plane now, we're told that this is equal to 4. Okay? So we've seemingly got a contradiction going on. For any x on the plane P, when I dot it with n, I get 4. I don't get 0. So how can they be perpendicular to each other? You know, two vectors are perpendicular if and only if their dot products are 0. This dot product is 4. And it's kind of subtle. Okay, it's really subtle what's going on here. I'm going to need to show you on GeoGebra what's actually going on. So bear with me. Here we are. So here's our plane. Alright. So our plane is going to come in and look like this. Okay. So here's our plane. Okay. Now, if I plot the normal vector 2 minus 1, 3, right, we can see that it is perpendicular to the plane. Okay, these right here are right angles, definitely. So this vector is perpendicular to the plane. So why, when I take the dot product, am I getting an answer of 4 and not 0? Well, if we take two vectors on the plane, okay, let's say v in 3, 2, 0. You can check yourself that if you plug 3, 2, 0 into this equation here, you do in fact get 4. So v is on the plane, and v looks like this. Okay? Alright. And then I got another vector w. Again, this is on the plane, and you can check it yourself if you want to. If I put it there, you can see this is w. I have w and v. Now the important thing is to notice that they're not on the plane. Okay? They're starting at the origin and their tips are touching the plane, but they're not sitting on the plane. And so of course, right, if we look at it from a different angle, you can see that these vectors are definitely not perpendicular to n. Okay? So what's going on here? Well, v and w and vectors are not on the plane. V and w and points are on the plane, right? So if I plot the point v, you can see the point v that's on the plane. But the vector v is a vector that starts at the origin and touches the plane. If I want to get a vector that's on the plane, I need to define a new vector called u, which is going to be w minus v. Okay? And we can see that this is kind of getting a bit better, right? It's not sitting on the plane just yet, right? But this vector isn't actually parallel to the plane like that. And so if I take my u and I, sorry now, what am I doing? Because I'm editing f. I want to edit u. Okay, here we go. So what I'm going to do is I'm now going to take the starting position of the vector u, which by default is the origin, 0, 0, 0. I'm going to move the starting point to the point v, okay? Just because v is a point on the plane. And you can see now alright, the vector u very much hits on the plane. Okay? I want you to take note here of vector u. -3, 6, 4. Okay? Jump back into Sketchpad. So now, if I take n and I dot it with the u vector that I've just found, that's going to be 2 minus 1, 3 dot -3, 6, 4. And so this is equal to 2 times -3 into -6. -1 times 6 is another -6. And 3 times 4 is 12. Okay, precise like this. And you can see that this, in fact, equals 0, like we want. So there's nothing wrong happening here. What's wrong is our assumption about what it means to be a vector on the plane. Okay? Just because the point satisfies the plane equation doesn't mean that the vector connecting the origin to that point is on the plane. In particular, a vector is on the plane if it's the vector between 2 points on the plane. If it's a vector starting from the origin, it definitely can't be on the plane, unless the plane goes through the origin. And you'll notice in our plane pi here, this plane don't go through the origin. Let's see that. So if I take my plane P here, I'm going to hide everything. Take my plane P, and instead of a 4 at the end there, I'm going to give it a 0. How does that change things? Well, now our plane has moved, and it's very clearly going through the origin. And so now, if I fill in V and W, we can see, actually, that doesn't work. Never mind. But if you were to take a point that satisfies this equation, the vector and the point would both be on the plane. Okay? That's the main thing I'm saying here. And so if I were to take this plane, and now if instead of letting it equal 0 or 4, I'm going to let it equal some number A. That's going to work. And now I can adjust what A is to my liking. So if I shift A, here, no idea why this isn't working, but anyway, let's not try and be clever here. Okay, GeoGebra is clearly much cleverer than me. So if I make this 4, you can see what happens in the plane shifts, okay? But what doesn't change in the direction the plane is oriented. All that changes is I move the plane up or down or left or right some amount, but I don't change the angle of the plane at all. If I make this 10, you need to shift the plane, right? And it's shifting the plane along the normal vector, the orange guy here. So if I make this -5, you can see it just looks like we've shifted it down the normal vector by 15 units. And so of course now, let me switch back again. So of course, it makes sense why these two planes here, okay, this guy and this guy, it makes sense why they have the same normal vector, okay? Because changing the 4 and the 0 to any other number, it's just pushing it up and down the normal vector. So the normal vector is not changing. The angle of the plane is not changing. All that is changing is where the plane is sitting in your coordinate space. So hopefully that clears up stuff. I kind of belabored that point, but sure look. Sorry. Well, let's talk about the rest of the question. Is the line L perpendicular to the plane P? Okay. Let's jump back into it. So if I just make this 4 again, and now I'm going to draw the line. Okay, I have it here. Now you can see that the line is definitely not perpendicular or parallel to the plane because the line cuts through the plane. Okay, at this point right here. The line goes through the origin. Remember that for later now. But the main thing is that you can see if the line were parallel to the plane, then of course it would be perpendicular to n. Okay, this would be a right angle right here. It would be perpendicular. But that's not the case. Okay, not at all. The line is also not parallel to n, and we know that because it's not a scalar multiple of the normal vector. And that's easy enough to show. I just thought visualizing what's going on here might help. This is why we're justified when we're asking if the if we're asking if the line is perpendicular to the plane, that we don't even need to worry about the plane at all. We can just talk about the normal vector, because the normal vector contains within it all the information we need about the plane. All of the information we need about the plane. Okay? So that's part C. Now for D and E. We have to prove or disprove that the plane P is a subspace of R3. And then we have to prove or disprove that the line is a subspace of R3. So we need to talk about a property of subspaces. Subspaces, okay, in particular, the only subspaces you talk about in this module are linear subspaces, but subspaces must contain the origin. Okay, and you can frame this in multiple ways. They must contain the origin, slash they must contain 0, slash they must contain the 0 vector. Okay, strictly speaking, I guess the 0 vector is the best way to describe it in linear algebra, but you get the idea. For it to be a subspace, it has to have 0, amongst other things, but to be a subspace at all, you have to have 0. So, let's check if the plane has a subspace. Or sorry, check if the plane is a subspace. So the plane P is 2x1 minus x2 plus 3x3 equals 4. In 0, 0, 0, or if you want 0, 0, 0, an element of P. Okay? And I'm just going to be, I'm being lazy with the notation here. Okay? You all, of course, know that the proper way to write this is like up here. So P is the set of all vectors or points in 3D space that satisfy this equation. So if 0 is a part of our plane, it should satisfy this equation. Let's check. Well, if I do 2 times 0, I take away 0, and I add 0, that gives me 0, which is not equal to 4. Okay? And to be a part of the plane, it should be equal to 4. Therefore, 0 is not an element of P. Alright. Sorry for mixing notation so much, but you can't write 0 and 0. 0 is not an element of P. Therefore, P is not a subspace. That's all you have to do, okay? When you're asking something is a subspace, the first thing you should be checking is 0 a part of your is 0 a part of it. If it's not, then you can immediately go, well, it's not. Or it didn't. Okay, done at 0, not subspace. Now, again, if we were to think about this in relation to this other plane, pi, right, instead of it being equal to 4, equal to 0, obviously now, if we check if 0, 0, 0 is on this, of course it is. 2 times 0 minus 0 plus 3 times 0 indefinitely equal to 0. Okay? And you saw in GeoGebra that when I typed in this equation instead of this guy, that this equation contained the origin. The plane went through the origin. And so that's why it's a subspace when you have the condition equal to 0, and it's not a subspace if you have the condition equal to anything but 0. Okay? So planes are subspaces if they have 0. If they don't have 0, they're not subspaces. So that's part D. And part E is basically the same thing. Okay? Lines are subspaces only if they have 0. So let's think about our line. T times minus 2, 0, 1. So L is defined by the equation T in minus 2, 0, 1. In 0, an element of L. Well, it definitely is. Consider T equals 0. Then I guess minus 2 times 0, 0, 1 times 0, which of course is the 0 vector, the origin, exactly what we wanted. Okay? That's how easy this is. I think for this module, it's fine, right? If you're given a plane or a line, to check if they're subspace, you just need to check if 0 is on them. Okay? It's not necessary to check the closure under addition and multiplication, because you can very easily prove that for a line to be in subspace it has to have 0, and for a plane to be in subspace it has to have 0. Other than that, I would just warn you against looking at sample test solutions when you're doing a different exam, because this trips up a lot of people, because in the sample exam the line was slightly different. I can actually pull it up, you know. So the sample exam that Klaus gave you, L was different. Okay, L was defined to be 2, 0, 1 plus T times 1, 1, 1. Okay, and of course this doesn't go through the origin. If T is 0, well then I'm at the point 2, 0, 1. And there's no value of T that I can fill in here to get this vector to be 0. Right, I can't take away 2 here and 1 here, because this vector is not a scalar multiple of this vector. So in the sample test, the line was not a subspace. In this test, however, because it contains the origin, it is a subspace. Well done to people who copped that. If you didn't cop that, I understand, right? It's an exam. You've only got an hour and a half. It's not, you know, your brain isn't slowly thinking through the abstract concepts and making connections like this. Now that's question 1 finished. We'll move on to question 2. I think question 2 was fine. Okay, should all be able to do this, right? Finding T of 1, 2, 3. And you just, for anyone who doesn't know, you just break 1, 2, and 3 down as 1, 0, 0 plus 2 times 0, 1, 0 plus 3 times 0, 0. Now, what a good few people did was they made some simple algebra mistakes here. Nothing you can do about them other than practice. But just in an exam, just be cautious that, you know, you are likely to make a mistake in the multiplication. Just make sure you follow stuff through and you recheck it. You should be fine. Determine the image. This should be fine as well, depending. So the image of t is going to be the linear span of the three vectors. Okay. So image of t is going to be the span of the columns of t. And in particular the entire column. Now, what you need to be careful of is that what if one of these columns is a linear combination of the other two? And in this case, and in the case with the sample test, that's true. So I can write this column as a linear combination of this one and this one. It's not too hard, right, if you think about it. I've got a -2 here, and I've got a 1 and a 3 here. There's only so many things you can do with these two vectors to make a -2 in the first thing. And then the bottom two things will follow. Part C, want to show that image of t into subspace 4-3. You know, like, I don't mind you copying this directly from the sample test, as long as you're learning. Okay, as long as you understand this. The image of any linear map is always the subspace. And I'm just going to prove it now in front of you, so you're forced to see it. So if I take an x and a y in the image of t, I need to check three things. I need to check that 0 is in the image, right? For it to be a subspace, it has to have 0. I need to check that x plus y is in the image for any x and y. And then I need to check that any scalar multiple of anything in the image is also in the image. Okay? So what sometimes in linear algebra we do is we combine these two conditions. Okay? Let's call it condition 2.5. You can check if lambda times x plus mu times y is an element of the image of t. Okay, lambda and mu are scalars. X and y, of course, are vectors. Okay, so if you were confused by seeing this in the sample test solution, don't be. This is just a way of combining these two conditions, so I only need to check one of them, you know, instead of two of them. I'm going to do it the long way. I'm going to check all three. So is 0 an element of the image of t? Well, if t is a linear map, and you can go back and check this, right, in the very start of your course, should be there, then you know that t of 0 is always 0. Okay, just a fact of being linear. T of 0 is 0, always. So 0 has to be in the image of t, right? 0 gets sent to 0. You might have more things that get sent to 0. You know, your kernel might have 500 different vectors a part of it. In that case, then t maps 500 different things to 0. But doesn't matter. 0 is still in the image. Now, this condition here. I'm very messy now. I'm very messy. So don't be copying down what I'm doing directly. If x and y are in the image of t, then up here I assumed x and y are in the image of t, which means that x should be can be written as some t times v. Similarly, y can be written as some t times w. Okay, they're in the image of t. T sends some vector to them. Well then, x plus y is going to be tv plus tw. And now, t is linear. Therefore, in this equation, on the right-hand side, instead of applying t to v and t to w separately, I can apply t to v plus w. This only works if t is linear. Being able to go from here to here is a property of linear maps. So x plus y and t of v plus w. Well then I'm done. T maps the vector v plus w to x plus y. So x plus y has to be in the image of t. Fine. And then the last part is going to be lambda times x. Well, I know x is in the image of t. So x is tv. What about lambda x? Well, I just multiply by lambda on both sides. Alright? But t is linear. Okay, t is linear, so I can bring constants. T is linear. I'm not going to write it again, just going to put a thing there. T being linear means if I have t lambda x, I can always bring a scalar outside of the map. Like that. So here, there's no reason why I can't just bring the scalar inside and get t of lambda times v equals lambda x. Well, now I've found a vector, lambda v, which gets mapped by t to lambda x. So lambda x has to be an element of the image of t. And so I've checked all three things, right? I've checked that if x and y are in the image of t, then these three things are true. So if you want, just in practice, without looking at Clausen's solution, try and prove what I just proved, but by using the combined condition, right? 2 and 3 combined condition, and just means you can prove it faster, I guess. I think that was all of question 2. Oh yeah. I actually want to do something else. Which one? Illustrate something important. So the image of t is always a subspace. Right? Always a subspace if t is linear. But t has to be linear. T has to be a linear map. Okay? We're in linear algebra. The image of t is a subspace if we're only dealing with a linear map. Another interesting thing is the kernel of t is always a subspace. It's always a subspace. Again, t has to be linear. So if you're someone who's sitting down right now and you're thinking, why does it matter what the image and the kernel are of a linear map? One of the most important things that we can do in math is try and find subspaces. Okay? Subspaces are important, right? They're like, it's like we're taking all of R3, and if we find a subspace that we're interested in, then we don't need to worry about the rest of R3 anymore. Okay? The three properties of a subspace essentially mean that if we're looking at stuff inside the subspace, we don't need to worry about anything outside. The subspace is its own self-contained linear space. You can't get out of it. We can just deal with that. And that's useful in maths. Because what if I don't want to deal with an entire space of really complicated things? What if I just want to look at a subspace of nice things, right? Not so complicated things. Well, I have to show it's a subspace first. And the good thing about linear maps is that the image of the linear map and the kernel are always subspaces. So if we're thinking about R3 or any other vector space and we want to come up with subspaces, all we really have to do is come up with linear maps. You know? If I come up with a linear map, then I get two subspaces for free. Its image and its kernel. You know, if you want to come up with 20 subspaces, you just need to think of 10 linear maps. And that's way easier. So that's why that's important. Another thing you could try and check if the kernel of t is indeed always a subspace, right? The proof is pretty similar to this, right? Just think about what the definition of the kernel is and use the fact that t is linear, right? You get it in 2 seconds. Now, that's question 2 wrapped up, at least all the common mistakes in it. Question 3, there weren't that many mistakes at all, to be honest. So part A, reduce it to echelon form. Okay, reduce your matrix A to echelon form. If you can't do this, right, I understand making simple mistakes. Row echelon form is hard, okay? It's hard to know how to reduce this. But if you can't do that, you really do need to practice, okay? It's just something you need to know, right? You're taking a linear algebra module. Row reduction is one of the most important things to come out of linear algebra. It's essentially the reason why linear algebra came to be, because you use row reduction to solve simultaneous equations. So seriously, you should know how to row reduce at this point. If you don't, go on and practice. Plenty of resources online. You can email me, you can email Klaus, you can email whoever you want. You know, any math lecturer is going to be happy to help you, right? If you want me to do a tutorial where I just do row reduction for an hour, I'm happy to do that if it helps, okay? So just be proactive in your learning. Just learn how to row reduce. It's not that hard. Part B is fine. Okay, augmented matrix, let it equal 0. Your row reduction gives you nice, easy equations. And then in this question, you will have 5 equations with, sorry, you'll have 3 equations with 5 unknowns. So you'll have 2 degrees of freedom, and that'll allow you to get the solution here. And then that's very easy to turn into a basis for the kernel. Now, something I noticed, right? The kernel in this question, and the kernel in most things, it's usually the span of vectors, right? Sometimes it's the span of just one vector, v1. In this question, it was the span of 2 vectors, okay? If these vectors are linearly independent, then you know that the dimension of the kernel of T is 2, right? The dimension is just the amount of things in, or sorry, the number of vectors that you need to take the span of to get it. Okay? So as long as these are linearly independent, you can just count the amount of vectors in here, and that's the dimension. For some reason, multiple people were scribbling out there 2 and putting 1. I don't know why, right? Again, it's an exam, panicking, overthinking, but it really ain't just this easy. Okay, you just need to count the amount of vectors that generate it, right? That when you take the span of them, you get the kernel. And then so for part D, the rank nullity theorem, that's fine. So we're mapping from OR5 to 4. So that means that the dimension of our domain, which is 5, right? The dimension of OR5 is 5, is going to be the dimension of the image of T plus the dimension of the kernel of T. And you know the dimension of the kernel of T is 2. So you bring this over and you get that this thing has to be equal to 3. You know, no other choice. It's that simple. Okay? Don't overthink the rank nullity theorem. It really is just as simple. You know, it's profound. It's weird. It's hard to prove when you're starting linear algebra, but, you know, it's fine. You know, at the end of the day, it does make sense. Okay? If I'm starting off in 5 dimensions of space, and my map is taking me to somewhere else, well then, either those dimensions are going to turn into where the map goes, or to where the map makes them equal to 0, i.e. destroys them. I've got 5 dimensions. The map's either going to take me to 5 dimensions, or it's going to take me to something less than 5 dimensions and destroy the other ones by sending them to 0. That's the rank nullity theorem in a nutshell. And that's question 3. Question 4. Okay, in the sample test, you were asked to show that W1, W2, and W3 are linearly independent. Okay? But in this question, in this exam, you got asked to show they're linearly dependent. So you do a different thing entirely to what you would have done in the sample exam. In the sample exam, you show that the only solution to this equation, Okay, this is linearly independent. So if they're linearly independent, the only solution is that lambda 1, lambda 2, and lambda 3 are all 0. Okay? This is independent. The vectors are independent of each other. You can't add them together to make 0 unless these lambdas are all 0, right? Which is trivial, right? Of course, if lambda is 0, it's going to be equal to 0. There's no other way to do it, though. If they're dependent, then this isn't true, okay? So in particular, if they're dependent, then what I could do is I could bring these guys to the other side of the 0. Okay, lambda 2, W2, with lambda 3, W3. And then I can divide by lambda 1. Okay? So this would be linearly, so this would show linear dependence. So why? Well, notice that if they're linearly independent, that means the only solutions are that all the lambda are 0. So if I tried to do that here, I'd be dividing by 0, which is a problem. You can't divide by 0 in math. So if vectors are linearly independent, you can't write the vectors in terms of one another. That's the main thing about linearly independent. You can't write them in terms of the other. So in the sample test, you were showing this. Okay? You were showing that this is true. The only solutions are lambda equal to 0. But this just isn't true for this question. W1, W2, and W3 are linearly dependent. Okay? You can actually write them in terms of one another. And that should be fine to see. Okay? I'd say if you're going to be kicking yourself when you see how easy this is. So W3 is minus V1 plus 2V2. Okay? I want to show they're linearly dependent. Well, all I have to do is show I can write one of them in terms of the other two. In particular, if I take W3, well, I want 2V2. V2 is a part of W2. So I'm going to say W3 in 2 times W2. And now I want to change the V1 to a minus V1. So I just need to subtract 3 times V1. Alright. 3 times W1. So if we check what this is, 2 times W2 is 2V1 plus 2V2. And then W1 is V1. So I get a minus 3 times V1. Which, indeed, right? 2 minus 3 is minus 1. Okay? So, to show that they were linearly independent, what am I doing? All you have to do is write this down. Okay? That's literally it. I can write one vector in terms of the other two, so they're linearly independent. Sorry, they're linearly dependent. If I can't do that, then this will be true, right? The only solution to this equation will be lambda are all 0. Okay? That's independent. What I would recommend you all doing is sitting down and comparing this question to the question on the sample test and seeing why there's a difference here. I'll give you a hint, or basically the answer. In the sample test, you had an extra vector here, V3, and W3 had a V3 in it. Okay? So in the sample test, you had V1 in W1, you had a V2 in W2, and a V3 in W3. So they all had different unique things in them, so you would never be able to write W3 in terms of W2, because there's no V3 in W1 or W2. How can you do that? So that's different. The only thing I can say here is I hope you've learned now something, and that you won't make the same mistake. I can offer you some advice, which is to just read the question in future, or just read them more carefully. Know your independence from your dependence, and don't mess up in saying it like I just did. I don't think anything else to talk about with regards to the test. Just checking my notes. If anything, no. No. There isn't. So that's it. Like, comment, subscribe for more tutorials, and I'll see you guys after Easter.